We are ANRV. That stands for Autonomous Naval Research Vehicle. This is our vehicle. The ANRV.
Get the slides. So, okay, so points on the slides.
All right, it's not gonna play.
Really?
No. You can drag it across.
Yeah, drag across.
This is our. Ryan made an AutoCAD 3D diagram of our vessel. It's not to exact specs because it's really hard to do that, but it's.
No, it is to exact specs.
Oh, it is to exact specs. He just added things that are ridiculous. Like this thing is supposed to hold stickers apparently for all the people who donate parts to us.
And waterproof.
And waterproof.
Very nice.
This is showing it being put together.
Yeah.
Different angles.
Yeah, that's why I said it's not to spec. The platform isn't to spec because it's ridiculously high.
Most of the green stuff is actually plastic. It's a polycarbonate, so it's not weight. The weight is all in the center and about even. With the CAD design, you can do weight, center of gravity, you can do heat and pressure and all that kind of stuff too, and it checks out in all those tests. But, yeah, that's right on.
All right, our goal for the project is to build, design and build a fully autonomous catamaran that is capable of navigating via GPS to a specific location, sending a magnetic retrieval unit, MRU, to Lake Florida and pick up Ferris Adams, float for more than 48 hours, and operate at full capacity for over 2 hours.
That should be van, not Ben.
We did some testing for the flotation.
Yeah, we did 48-hour testing this past weekend, and it lasted 24 hours through a rainstorm, and it lasted 48 total hours without taking on any water. This is the hardware we decided to use. We're using the same microcontroller as they are, the Arduino Mega 2560. We decided to go with a lithium polymer battery, a 22.2 volt, 4 amp per hour battery. This will give us enough power to run pretty much all of the components that we need to at one time. This will hold from 6 to 20 volts. This takes our DC motors, our propulsion motors are going to be 14 volt, 23 turn neutral motors. So they'll actually, and they say that the best rate to run it at is like 10 volts at like 20,000 RPMs. It's about 1.5 to 2 amps per volt output. And then this is our water resistant ultrasonic rangefinder. That's what we're going to use to send the ping down to the bottom of whatever lake or reservoir or whatever body of water we're at. And first of all, it's going to get a depth reading, so we'll be able to know from surface to bottom what we're dealing with.
I want to point out real quick, our battery does come with an indicator to show how, like, the levels of the batteries.
And the chargers.
Good.
We also are going to use a Parallax GPS receiver module, which is actually an Arduino Shield, which actually has already been tested for the Arduino microcontrollers, and it has all the GPS locations already preloaded in there for the code, and you can set 20 different GPS points for boundary or specific locations that you want to check. And then the motor controller, which is this one right here. We chose this one because it's a shield for the specifically built for the Arduino, and it has 4 600 milliamp H bridges already built into it, so it'll hold the 4 servos, the 4 DC motors that we need. We're going to do the two DC motors, run those in parallel, and then we'll run the 2 DC motors that we're using for the winch. We're going to run in parallel as well, so we can pull the least amount of voltage off of our battery. And then we're also going to integrate a wireless module. We don't have a picture of it on here, unless you do. Is it this one?
Yeah.
Well,
it's the Zigbee. It's the one.
Oh, the Zigbee. Yeah. So this wireless module actually goes up to 300 feet outdoors, unobstructed, 100 feet indoors. And basically what we want to be able to do, it only wants to do a couple functions, basically a start switch, off switch, an auto kill switch, and kind of a distress signal where we can, if we want to, we can send it out. If we see something coming towards it, the weather gets bad and we want to automatically bring it back, then we can send out a distress signal, it'll stop what it's doing and come back to where it originally came from. And then just a graphics LCD display on board just to output, you know, temperature, internal core temperature, make sure nothing's burning up, you know, what GPS location it's at. It can record what last GPS location it was at before it came back, all that stuff.
And here's kind of a weird layout of the software. But this is going to be our microcontroller. It's going to be interfaced with the GPS, motor controller, and ultrasonic rangefinder. And then also the wireless communication module. And we're not sure the output of the GPS and the rangefinder, but we're going to do a lot of testing with that and see what kind of output we get and work with that to create the output we want.
Prototypes and testing. We right now have a prototype that we have already built. It'll be in a video later, but it's a scale model made out of PVC. We have tested it, as we said, with up to 40.
Well, it's like safely because we didn't build the cross members from hole to hole. We just built the platform and then built over the top of it. So there's kind of no mill support.
And we tested it; it didn't pass.
But we were able to get 35 pounds onto it before it started to bow. So basically, from that, we can assume that if we put the cross members across from hole to hole, it will not only hold that 35 pounds without going out, but it will be able to hold at least 15 to 20 more pounds because it barely went down in the water. And then, yeah, we kept it. We did a 24-hour test, a 48-hour leak test. Everything passed. And the one thing we did decide to do is lower the platform from 12 inches high to 8 inches high, just to, you know, make sure that it doesn't blow over, just in case there are high winds.
I haven't fixed that on the animation here.
So this is the cost for everything, or all the parts we found so far. We might be looking around locally to see if we can find any maybe scrap aluminum that we can use instead of paying for that, so our price could go down. Our total price right now is going to be around $750 for all the parts.
Yes.
Tabular presentation would make that a lot easier for your audience to assess.
Yeah.
Just put it in some sort of a, you know.
Yeah.
It's like movie credits.
Yeah.
Yeah.
For next time.
Yeah.
We also are sending letters to distributors and the companies themselves for sponsorship deals. And we already have a letter written representing ourselves.
There's actually a hobby place. It's called Hobby Town. It's over off 92nd in Wadsworth. They actually specifically have stuff for RC cars, RC boats, and all that stuff. So we're going to try to go in there and see if they can hook us up with parts, and we'll just stick their sticker on our boat. Because they have every single part. This is our timeline, which we printed out the Gantt chart for you because it looks horrible up here. So phase one is basically this first 8 to 10 weeks is our research, our written proposals, making up our diagrams, pulling up all of the whatever. Assuming we get that done, phase two is going to be our fabrication, which is going to be actually probably going to take only 3-4 weeks to fabricate the actual hull, maybe only a week once we get the parts to fabricate the hulls, get them welded, get them done before we can start integrating, start testing the individual DC motors, making sure they work, testing the software to make sure that there's no bugs in the software. We can run each one individually with its individual software before we integrate all the software together. And then phase three is going to be basically it's going to be our full functionality testing once the entire boat with the DC motors, the microcontroller, the winch, and everything is attached. Then that's when we'll start our full functionality testing, which I'm assuming is going to take basically as much time as it needs to take to be able to get it perfect. And then obviously phase four is just the final testing, final project, and the papers and stuff.
And also in phase three, if we have enough time extra, we might add some more functionality. We're not sure what we'll go with yet, but if we have enough time for extra, we might do that too.
And then final paper, final test.